Alright, hello class. Today we're looking at lesson 17, which is all about dividing polynomials. Alright, so this is sort of what we looked at. We've kind of looked at this before with rational expressions, but we're taking it a step further. This is also furthering that question we started with in the last lecture, which was what do we do when we can't factor a polynomial, right, to find its roots? What if we can't factor? How do we start by factoring? How do we start finding roots if we can't factor? Okay, so one of the steps towards that direction is actually dividing polynomials. Okay, so let's start by reminding ourselves of long division, that we can actually apply long division to polynomials. Okay? And so we can set up long division in the way that we usually do, but with, say, polynomials. So, for example, let me set up a problem for you, and then I think it's easier to just kind of show you with an example than explaining it before I do that. So let me set up an example for you. I'll be right back. Okay, so what we want to do is divide these two polynomials. So I'm going to take 15x squared plus 16x minus 8, and I'm going to divide it by 5x minus 3. Okay, and so we can actually set this up with our normal long division, if you remember from back in the day, right? Remember this, where we'd set up our little division, long division symbol. I'm dividing by this 5x minus 3. And we just do our long division like normal. I think the thing that confuses people or trips people up ends up being the changing the signs and subtracting. But yeah, so we just go about it like we normally would. So what we want to do, we have 5x minus 3 here. I want to find something that if I multiply 5x by it, I'd get 15x squared. So to multiply 5 by something to get 15, I would need a 3. And to multiply x by something to get x squared, I need an x. So 3x is what I need to multiply 5x by to get 15x squared. And then we also multiply it by the whole thing, so both pieces. So this negative 3 as well, so I'll get a negative 9x. Okay? So then, if you remember, back to your long division, what do? Once you multiply the thing, you actually subtract. So we are going to subtract these values. So what I like to do, some people write a subtraction out here. I actually go through and I change the signs directly. Okay? Because remember, if I'm going to subtract a minus, it's going to turn into a plus. So I'm going to subtract the 15x squared, right? And then I subtract the negative 9x, which becomes a plus 9x. Okay? So this ends up being, this comes out to be 0, and here we get plus 25x. Okay? Then we bring down this next piece, right, this minus 8. Hopefully this is looking familiar. Okay. And now we do this process again. I want to find something that I can multiply 5x by to get 25x. Well, to multiply this by, if I choose 5, right, 5 times 5 would give me 25, and I already have the x. Right, so 5 times 5x is going to be 25x. And then now 5 times the 3 will be minus 15. Okay. Then we go through and we change our signs. Okay, changing my signs, the 25x's cancel, and that's always going to happen, right? That piece, we set it up to cancel. And then here I have a negative 8 plus a 15. That's going to come out to be 7. And we try to do this process again, and here's what happens. If you remember, back when you did long division in the past, a lot of times you would have a remainder. So here, now the question would become, I need to multiply 5x to get 7, and there's no way to do it because we would get an x here. We don't have an x here. So what happens is this just ends up being the remainder. Okay, and this is the quotient. Okay. So what this means is that this 15x squared plus 16x minus 8 divided by 5x minus 3 ends up being, it's the quotient, so 3x plus 5, plus the remainder, 7, over the divisor. Okay. So this, again, is the quotient. This is the remainder. So when we divide these polynomials, we get 3x plus 5 with a remainder of 7, and the expression ends up being 7 over 5x minus 3. Okay, another way to write this would be like this. This 15x squared plus 16x minus 8 all over 5x minus 3 is this expression here, the 3x plus 5 plus 7 all over 5x minus 3. If we multiply this, might multiply everything by this 5x minus 3, right? Well, what's going to happen is the 5x minus 3's will cancel every step where we have a fraction. So let me actually write this out. Right, so if I multiply this by 5x minus 3, these pieces cancel. I have a 3x plus 5. That times a 5x minus 3. Well, nothing cancels there. That just stays like that. But then the plus 7 piece, well, the denominators cancel there. So multiplying by what you're dividing by everywhere, once you've gotten this expression, cancels out all the fractions, and so what you get is a 15x squared plus 16x minus 8 is equal to a 3x plus 5 times a 5x minus 3 plus 7. Well, okay. This is almost factored, right? In fact, this would have been factored if we had had a remainder 0. Right? So what division allows us to do if we suspect, say we don't know how to factor something, but we suspect that we have a particular root, okay? Or we have something that might give us a remainder 0, we can use long division to give us a factored form of it. If we do have a remainder, we just end up with a plus 7. We could maybe move that around and do some stuff if we needed to. But let's see what happens when we actually have a remainder of 0. All right, so let's divide 4x cubed minus 4x squared minus 9x minus 15 by 2x minus 5. Okay, so we're going to use long division here. So 4x cubed minus 4x squared minus 9x minus 15. One thing you need to be sure about, if you're missing any pieces, like if I was missing an x term, make sure you put a 0x in there, just so you are able to utilize every piece. We'll look at an example that deals with that, of course, but make sure all parts are, or all possible x powers are dealt with. we're going to divide this by 2x minus 5. Okay. So I want to find something that if I multiply 2x by it, I will get 4x cubed. So I'm thinking 2 to get me the 4, and an x squared to give me the x cubed, right? Because when we multiply, we get a 4x cubed. Okay, then we multiply it by the minus 5 to get a minus 10x squared. Okay, then we go through and change our signs. So I subtract by the 4x cubed. And then here it's a negative 4x squared plus a 10x squared, so we'll get a 6x squared. And then we're going to drop down the negative 9x. Okay, again, this works very much like long division did with just numbers, except now we have x's and things like that. Okay. All right. Now I want to find something I can multiply 2x by to give me a 6x squared. Well, I think a 3 will give me the 6, right? And then the x squared, I need another x in there to give me the x squared. So the 3x times 2x will give me a 6x squared. And then I do multiply by the negative 5 as well, and that's going to give me a minus 15x. So once again, I go through and change my signs, because I need to just subtract by everything. So the 6x squareds cancel, and I have negative 9x plus 15x, which will give me 6x again. Okay, well, not 6x again, but another 6 again. Then we're going to bring down that minus 15. Okay, and then we're going to repeat our process again. All right, so now I need to find something that will give me 6x to multiply 2x by. So I think just plus 3 will give that to us, because we already have the x that we need. So 3 times 2x is going to give us 6x, and 3 times negative 5 will give us minus 15. Okay, so we go through and change our signs. This 6x minus 6x will cancel to give us 0, and minus 15 plus 15 will cancel to give us 0. So we have remainder 0 now. Okay, so what this means is that if I take 4x cubed minus 4x squared minus 9x minus 15, and I divide it by 2x minus 5, well, we always get the quotient. So here's the quotient. Okay. So we're going to get the quotient, which was 2x squared plus 3x plus 3, then plus 0 over the divisor 2x minus 5. All right, whenever you do division of polynomials, right, like a polynomial p of x divided by d of x, you always get the quotient q plus the remainder over the divisor. All right, that's just always what happens. Well, this 0 over the 2x minus 5, that's just 0. Okay. So if we rewrite this as a fraction, right, this is the same thing as 4x cubed minus 4x squared minus 9x minus 15 all over 2x minus 5 is equal to just 2x squared plus 3x plus 3. Right now, if I multiply both sides by this 2x minus 5, so multiply by 2x minus 5, or just move it over, right, what you'll end up with is 4x cubed minus 4x squared minus 9x minus 15 is equal to 2x squared plus 3x plus 3, all times 2x minus 5. And check that out. We have now factored this thing into this. Okay? Now looking at this, this might not have been something you would have thought could factor. Or actually, you might have thought you could factor this by grouping. Okay? If you tried to factor this by grouping, if your first group, you could take out a 4 and an x squared, and you'd be left with x minus 1. And then with the second group, you can actually take out a minus 3, and then you'd be left with a 3x minus 5 when you did that. Or, sorry, 3x plus 5. Which doesn't exactly help you when trying to factor by grouping, right? Because these don't match. But what we were able to do through long division, since we got a remainder of 0, we got a nice factored form here. And then we might be able to factor this a step further, or maybe not. This might be prime. If we remember our AC method, a times c is 6, we would need factors of 6 that would sum up to be 3 for that to be able to factor. I don't think it does. Yeah, there are no factors of 6 that I can think of that would nicely come together to give us a 3. Since we have 2 and 3 and 6 and 1, no, it would not work. If we had a 5 there, it would probably work. But now we are now able, using division, to actually factor this expression. Okay? Okay, now from here, I think I know what some of you are thinking. This process takes a lot of space, and if we have to do this to help us find roots, or to help us find zeros, or to help us factor, this is a long process. So what we actually have, since what we're really trying to do here is find roots, okay, when dividing, okay, by just an x minus an r or x plus an r, okay, we can use a simplified version of long division called synthetic division. Okay, so here's how synthetic division works. Suppose I want to take, we'll start with something kind of simple, x squared plus 5x plus 6, and I want to divide it by x minus 1. Okay, so first I will show you the long division, and then I'll show you how we set this up with synthetic division, just to show that we actually get the same thing out. Okay, so when we set up our long division, right, we do our long division symbol. I put x squared plus 5x plus 6. I put my x minus 1, and I want to find something I can multiply x minus 1 by to give me x squared. So x would do that, so multiply by x, I'll get x squared, and then I'll get a minus x. Alright, so then we go through and we change our signs. Right, the x squareds cancel, and I have a 5x plus x, so I get a 6x. We bring our 6 down, and then we repeat the process. I try to find something I can multiply x by to give me a 6x, and plus 6 would do that. Right? So 6, multiply that through, I'd get a 6x. I get a minus 6. And then I would go through and I'd change my signs. Minus, plus. And then, so the 6x's would cancel and I have a 6 plus a 6, so I get a 12. So my quotient is x plus 6, and my remainder is 12. Okay, that's all well and good, but it takes up a lot of space. Yeah, we want to find a quicker way to do this. Now, keep in mind, this is only going to work when we're dividing by things like this, an x minus 1, x plus 2, and x minus 3. The simpler types of problems, but that's fine, because if you remember, when we have it in complete factored form, polynomials in complete factored form end up looking like x minus 1 times x plus 2 squared times x minus 3, stuff like that. It's likely we'll have things like this if that's what we're looking for, right? If roots are what we're actually looking for, it's likely that's how we will find them. Okay, so this is actually a really important type of divisor, and it's also why we have a special form for doing this for this type of problem. Okay, so here's how we do it. We set up a division bar more like this. Okay, and what I do is I just take the coefficients of what I'm dividing by. So instead of saying x squared plus 5x plus 6, I put 1, 5, and 6. Okay? Then here, instead of putting x minus 1, all I do is I take the constant part, okay, just the constant part, and I put the negation of that here. Now, why the negation? Well, think of it this way. If x minus 1 is one of our pieces that gives us a root, if I set this equal to 0 and solved, I'd actually get x equals 1 as a root. Right? So we're actually putting a root here. The test root is what we would call it. All right, so this is actually the negative of the constant. Okay. Or the test root. Okay. All right, so what we do is we start by dropping down this first value. All right, so we drop down the 1. Okay. Now, what we're going to do is take this value, this 1, and multiply. Now, I'm going to multiply these two together, so I'll get 1 times 1, which is going to give me 1. Now, I add these values. Okay, so 1 times 1, I bring that 1 up, add, and I'll get 6. Now I take my test root again, multiply, 1 times 6, and carry up, so we get 6. Okay, then we add these values again to give me 12. Okay, so to write it in a less cluttered way, to write it again, I bring the 1 down, multiply, carry up. Then I add. Then I multiply, carry up, and add. Once you finish doing that, okay, then this final piece is our remainder. Then it goes constant x, and then we would go further. It could be x squared, it could be x cubed, however many values you have here, that's what you're going to end up with. So what that means is my x value is I have x plus 6, that's my quotient, and my remainder is 12. Hey, that's exactly what we got over here. Our remainder was 12, our quotient was 6, or x plus 6. So when we do this division, this x squared plus 5x plus 6 divided by x minus 1, we get x plus 6 plus 12 over x minus 1. I keep showing it like this because this is how MyLabs Plus asks you to write your answers. It's going to have a portion for your quotient, and it's going to have a portion for your remainder that goes over the divisor. Fair enough? Okay, let's look at an actual example that has something other than 1, because 1 isn't necessarily a great value to do this with. You know, that's just good one to start with, I guess, but let's look at one that's a little more interesting. Alright, let's look at this example. Let's say I want to do 5x squared plus 3x minus 12. I'm going to divide it by x plus 3. So remember, for our synthetic division, I'm going to take my coefficients, the 5, the 3, and the negative 12. I'm going to put those along this row. And then I'm going to take this value and negate it. Alright, it's always the negative of that. Okay? So, then we start by dropping this 5. Then we're going to multiply. So we always put a little x in a circle there. We always multiply and then bring up along the diagonal. Okay? So we'll negative 3 times 5 is a negative 15, and we bring that up here. And now we add these together. Okay, so the 3 minus the 15 will give me a negative 12. Alright, now it's going to be a negative 3 times a negative 12, which will be a positive 36. Okay, then the negative 12 plus the 36, we add these together, so we add along this line. And no, we did that here because we technically have a 0 there. But we add along this line. 36 minus 12 is going to be 24. Okay, so this is the remainder. This will be my constant. This will be my x. So what I end up with is my quotient, which we usually call cube x, but the quotient is 5x minus 12, and the remainder is 24. So this expression could be rewritten as 5x minus 12 plus 24 over 5x minus 12. There we go. What we've done is essentially we've taken now an operation that would be stacked and maybe have multiple lines and basically reduced it down to 3 lines. So it's really a safe space saver for very specific types of division. Okay, let's do a problem with synthetic division again. Maybe a little more lengthier problem here. So what we're going to do is divide using synthetic division. Okay, so we have 6x to the 5th minus 2x cubed plus 4. X squared minus 7x plus 3 divided by x minus 2. Alright. So, we're going to set our synthetic division bar up. And remember, we put all of our coefficients in. Now, keep in mind, we skipped one. We have 6x to the 5th and a 2x cubed, or negative 2x cubed. We don't have an x to the 4th. Right? So we would put a 0 in for that piece. We need to actually have that piece there somehow. So I'm going to put a 6 in for x to the 5th, a 0 in for x to the 4th, then a -2 for x cubed, and I don't think we skip anything else because we have x squared, x, and a constant. Right? So every possibility needs to be considered. Alright, so we have all of our pieces here. I have the 6, I have the 0, I have the -2, I have the 4, I have the -7, I have the 3. Put a +3. That might be a little redundant, but whatever. Now, this -2, remember, for the x -2, I put in a +2. Okay? So, we always start by dropping down that 6 and multiplying and putting that up here. So, the 2 times the 6 will give me a 12. I put that up there. And then we add these together. So I'll get the 12. And then now I multiply that by 2. So 2 times 12 will be 24. And now I'm going to add these together. So the -2 plus the 24 will give me 22. All right, and now we're starting to get into kind of larger numbers here. 2 times the 22 will give me 44, and adding those together, 4 plus 44 is going to be 48. Alright, then 2 times the 48 is going to be 96. Now minus the 7 gives us an 89. Right? And then finally this 2 times the 89 give me 178, plus the 3 gives me a 181. Okay, and there we go. We now have our string of values here. This last one is the remainder. Then we just escalate up. This is the constant, this is the x term, this is the x squared term, this is the x cubed term, and this is the x to the 4th term. Okay, so this division here, right, would come out to be our quotient, which is 6x to the 4th plus 12x cubed plus 22x squared plus 48x plus 89. Okay, then plus the remainder, 181, all over x minus 2. Right? And that is that. That is, now think about how long some of these took before, at least maybe lengthwise this way, vertically, how much space it would have taken to do this, and how we've condensed the work into a much more cohesive way of doing this. Okay, synthetic division is awesome and everything, but it only works for an x plus or minus some number. Now you can also kind of mess with things a little bit if you don't have that exactly, but essentially synthetic division only works when dividing by, say, x plus or minus some number. We're using little r for the remainder here, so just x plus or minus an a, right? Something like that. It's only going to work in situations like that. And it works because for this x, it's a 1x, so we really only need the same value to multiply, or to match the coefficient. We basically just need the constant itself, the coefficient itself, since we have a 1 times x. Okay, so if we're dividing by something different than this, well, guess what? We're we're going to have to go back to long division. Like say, for example, this 2x cubed minus 4x plus 9x plus 8 divided by 2x squared plus 2x plus 2. We have to use a long division here. Sorry. So we have to use long division. But I know that's a bummer, but actually, since we're dividing by something with 3 pieces, it's actually going to go faster than the other case where we just had the 2. In fact, the larger your divisor is, the faster you'll be able to get through the division. You may have noticed, actually, in, say, this example. I divided something that was a degree 5 polynomial by just an x, and we got a degree 4 polynomial as our quotient. Yeah. When we were dividing by just an x term, the degree that we ended up with went down by 1. Now, on the other hand, I'm taking x cubed something and dividing it by an x squared something. We should just get an x something. So actually, this should go fairly quickly since we have more pieces. But let me just shut up and we'll get to it. So since we have to do long division, let me set that up. I have my 2x cubed minus 4x squared plus 9x plus 8. And we're dividing it by 2x squared plus 2x plus 2. Okay. So now I need something that I can multiply the 2x squared by to match this 2x cubed. Well, x. Right? X times 2x squared will give me 2x cubed. And now I just multiply all the pieces. So x times 2x will give me plus 2x squared. And the x plus the, or x times the 2 will give me plus a 2x. Okay. Then I go through and change my signs. So it's not as easy this time, since I have pluses there already. But you can X that out, put a minus, as long as you just change the sign somehow. So the 2x cubes will cancel. This minus 4x squared minus 2x will give me negative 6x squared. Then this 9x minus 2x will give me 7x. Okay. Now we carry down the 8. And we do it again. Now I want to multiply the 2x squared by something to match this negative 6x squared. So I think negative 3 is in order. And negative 3 times the 2x squared gives me a minus 6x squared. And then we multiply the 3 by everything else. So the 3 times the 2x will give me a minus 6x. And the negative 3 times the 2 will give me a minus 6. Okay? Alright, now we can go through and change all the signs. Much easier this time since I'm changing all my minuses to pluses. The 6x squareds cancel. And now, well, nothing cancels as nicely as it should have before. We'll get a 13x and plus 14. Okay? And we're done. This is now our quotient. And this is our remainder. Okay, so this thing here comes out to be x minus 3 plus a 13x plus 14 all over this 2x squared plus 2x plus 2. And there we go, our quotient and our remainder. Alright, so I'm going to show you how we can actually use division to help us solve equations, to help us deal with polynomials, right? To help us fight with them, so to speak. Okay, so let's say we want to solve this equation. We have x cubed minus 5x squared plus 2x plus 8. I want to solve it, and here's the problem. We can't really factor this. I can't factor this by grouping in a helpful way. there's not much I can see just right off the bat to help me factor this. But here's what I do know. Suppose I know that -1 is a solution, right? And we can actually check that. We can plug that in and check to see if that's a solution, right? -1 cubed minus, you can't see what I'm doing there, minus 5 times -1 squared plus 2 times -1 plus 8. And yeah, when we plug in -1, we actually do get 0. Okay. What this means, if -1 is a 0, that means this thing should be able to factor into x plus 1 times something else. Okay. Notice I used q. I used that specifically. And I know that because, check that out, if I plug in -1, that goes to 0. So I have 0 times whatever in the world is left over, which comes out to be 0. So I know that this polynomial should be able to factor into an x plus 1 times something else. Well, actually, let me leave that there. So let's divide, okay, our x cubed minus 5, x squared plus 2x plus 8. And let's actually divide it by this x plus 1. Okay, and see what we get. Now, as we saw before, this using synthetic division is not going to be that complicated since we have a 1. Right, so I'll put a 1, a minus 5, a 2, and an 8. I'm not missing any pieces, right? I go x cubed, squared, x, constant, so I have all my pieces there. And remember, we change this to a -1 when we put it there. -1, -1. See that? The 0, the root? That's what I said when these are test roots. Now, when I do this division, since this is a 0, since this is actually a root, since I know that, I need to get a remainder of 0. I should get a remainder of 0 out. This should come out to be nice. But let's see. I'll drop this 1 down, do my multiplication. -1 times 1 is -1. And then I sum these up. So -5 minus the 1 will give me a -6. Okay? -1 times -6 is a positive 6. Now I'll sum these up and get an 8. Okay? And then this -1 times the 8 gives me -8. There we go. And look at that. 8 minus 8 gives me 0. So this is my remainder, 0, and then I'll get constant x squared. Alright, since we have remainder 0, that means this division here, which I can write like this, x cubed minus 5x squared plus 2x plus 8 over x plus 1 is x squared minus 6x plus 8. Okay. There's my q of x. There's my quotient. My remainder was 0, right, because I could put plus 0 over the x plus 1, but it's just 0, so we don't need to worry about that. So what that means, if I move this over now, right, multiply by that divisor, I get x plus 1 times x squared minus 6x plus 8. Right? There we go. So, using this synthetic division, since I already know one root, I can use that fact to divide it by that root, divide by the 0 using synthetic division, and now that has helped me factor, because the problem with this is I can't see how to factor this, right? Even if I split it into groups, factoring that by grouping, if I took out the x squared, I'd get an x squared times an x minus 5, and then here if I took out the 2, I'd get a plus 2x plus 4, that's not going to go anywhere, right? This doesn't factor nicely until now, okay? So, this x cubed minus 5x squared plus 2x plus 8 equals 0 is now x plus 1 times x squared minus 6x plus 8 equals 0. All right, now this piece should be able to factor. I want factors of 8, right, that sum up to equal negative 6. So they both need to be negative, and I'm thinking negative 2 and negative 4. So negative 2 times negative 4 is 8, negative 2 minus 4 is negative 6. So this, now we get x plus 1 times x minus 2 times x minus 4. And there we go. That tells me that x is equal to negative 1, which we already knew, 2, or 4. So we were able to find the other solutions using synthetic division to help us out, which is pretty cool, actually. This isn't that difficult to do with synthetic division. If you had to do long division every time, it might be a pain. But with the synthetic division, it's not. It doesn't even take as long as factoring does sometimes. Okay, it's just knowing this connective piece that helps you. Yeah. So the next question that we have is, okay, great, but how do we know that negative 1 is a solution? We can't just plug in a bunch of values till we get the right answer. We could be here all day. And what if they're fractions, right? So the next question becomes, is there a way we can find one root quickly? Sometimes there is, and then, you know, sometimes just by looking at it, you could maybe tell that you have a certain root. But in the next lesson, that's actually what we'll be doing. We'll be looking at how do we find roots. Okay, how do we find one root? Because once we find one root, we can use synthetic division to help us factor, and then hopefully from that point we can factor further. Yeah, like we did here. But the key is once we find one root, we're good because we can actually do a first step of factoring. So if you ever wondered how you can factor some of these more complicated problems out there, if you can find a single root, if you can find a single zero, that's really what you need to be able to get you there. All right, so that is all I really need to talk to you all about as far as dividing polynomials go. In the next section, we will take that next step to how do we find a root.